today, students. So in this clip, we're going to be going over the derivation of the law of cosines. Before we start, let's go ahead and take a look at some key formulas that you need to know in order to do this proof. Okay. So you need to note the following. You need to note that first of all, uh, sine equals opposite of a hypotenuse. Cosine, well, let's put the angle in there. Theta. Cosine theta equals adjacent to a hypotenuse. And tan theta equals opposite over adjacent. Okay? We're going to be making use of just these first two. But you remember SOHCAHTOA, right? SOHCAHTOA. The condensed form for these three formulas is SOHCAHTOA. So we're going to be using SO and CA in our derivation today. Alright? So that's the first point you need to note. Secondly, you need to know the Pythagorean identity, which is the fact that sine squared theta plus cosine squared theta equals 1. We're going to use this in the simplification of an expanded binomial. And then lastly, we need to know the Pythagorean theorem, which is a squared plus b squared equals c squared. Alright? So these are the three things you need to note that we're going to be making use of in our derivation. Okay? Alright, so let's write down the task. We're just going to be showing one variation of the law of cosine. So the task is to show that in triangle ABC, a square equals c square plus b square minus 2 bc cosine so a square is equal to c square plus b square minus 2bc cosine a. Alright, there are three other variations of the Pythagorean theorem of the law of cosines. Let me write them up here. We're just going to show this, but using the same approach we can use it to show the other ones. Okay, so we also have v square equals a square plus c square minus 2ac cosine b, and then also c square equals a square plus b square minus 2ab cosine c. Okay, the way I wrote this, I can remember addition commutes, right? So I could also write this as a square equals b square plus c square. This is how it's presented in most textbooks, minus 2bc cosine a. All right. So these are the three variations of the law of cosines. These two are exactly the same, only that I interchanged the b square and the c square. Okay. All right. So let's go ahead and prove this. So to start us off, we're going to draw a triangle. So let's draw ourselves a triangle that looks like this. Alright, so in this triangle that we have, we're going to label the sides in the following format. This is big A. If this is big A, then this is going to be lowercase a. And let's call this big B. If this is big B, this entire segment down here will be lowercase b. Okay, and then this is big C. Then this will be lowercase c. And let's say the altitude of our triangle is h. Okay, so this segment right here is h. So if that is h, then we can also do some other labeling. So I have h here. So let's call this segment from here all the way to here. Let's call that r. Okay, so from here to here is r. And let's call the point where the altitude hits segment AC, let's call that point D. Alright, so we have a triangle set up like this. Now we're going to write down some equations using SOHCAHTOA, right triangle trig, and also write another equation using the Pythagorean theorem, and then we'll combine the two and end up with the law of cosines. Okay, alright, so let's start off by taking a look at, we're going to focus our attention on triangle ABD. Okay, triangle ABD with reference to angle A. So this will be our reference angle right here. So this is a reference angle in triangle ABD. This side right here will be our opposite. H is going to be our O. And then this side will be a hypotenuse. Why do we know that's a hypotenuse? Because this is a right angle right here. And this side right here, segment R, will be our adjacent. Okay? Alright, so let's go ahead and write down an equation using right triangle trig. Okay, so in triangle ABD, we have sine A. What is sine in SOHCAHTOA? In SOHCAHTOA, sine is opposite of a hypotenuse, right? So sine of angle A is going to be the opposite, which is H, over the hypotenuse, which is C. Okay? How about we isolate C, get C by itself, get H by itself. So to do that, we'll multiply both sides by C, multiply this by C, multiply this by C, and then you're going to end up with, this implies that H, because these two cancel divide out, H equals C sine A. Okay? Alright, let's leave this the way it is. Now we're going to move on to, let's do the cosine of angle A, okay? It's the same triangle. What will cosine A be? In SOHCAHTOA, what does Ka mean? Ka means that cosine is adjacent of a hypotenuse, yes? So we have, this is the angle we're looking at. So the adjacent is R, and the hypotenuse is C. So let's isolate R as we isolated H. We multiply both sides by C, left and right. The C's cancel out. And this implies that R equals C cosine angle A. Alright? Okay, now we're done with this for now. We're going to shift our attention to triangle CBD. Okay? What can we say about triangle CBD? Well, this is a right triangle also. We have a linear pair right here. Angle BDA and BDC are a linear pair. Now, the entire segment is B and this is R. Then what do we have left? That's the question. Okay? So we know that this segment that's left right here, that segment, what's the measure going to be? Well, it's simply going to be the whole minus the part that we took out, right? So the entire thing is R. The entire thing is B, and then we took out R, so we're going to be left with. Let's call this segment red so we can focus our attention on what we're dealing with here. Okay, so make it red. All right, so that segment right there is going to be. This segment is going to be B minus R. Okay, because B is the entire thing, and R is the part that we took out from the entire piece. Okay, so this is B minus R. Now, from the Pythagorean theorem, we can do the following. All right, we can use the Pythagorean theorem on this right triangle right here. Okay, let me draw it on the side again so that you can see clearly what is going on. So triangle, I'm going to just extract triangle BDC. So let's go ahead and extract triangle BDC. Looks something like this. So we have this side is H, and this is B minus R, and this is A. Okay, so now using the Pythagorean theorem, what do we know here? Using the Pythagorean theorem, we know this is A, and this entire segment is B, and this is C. A and B are interchangeable because they're the legs, right? We know that A squared plus B squared equals C squared, right? So we can plug in these values here. So we're going to have A is H squared plus B is B minus R squared equals C squared, which is A squared. Okay? Alright, so we're going to use that for the second part of our proof. Just applying the Pythagorean theorem to triangle BDC. Okay? Let me label it here so we don't get confused. Triangle BDC. Alright, so let's write that down. In triangle BDC, we have, well, let's switch this equation around. We have A squared equals, that's a hypotenuse square, H squared, which is A squared, plus b minus r squared. Okay? Uh-oh. Let's redo that again. B minus r quantity squared. Alright, so let's see. Yeah, I just rewrote this equation that we just derived earlier. I just rewrote it over here, okay? So now let's go ahead and expand this equation a little bit. So we're going to have a squared equals h squared plus b minus r times b minus r, okay? So we expand b minus r and b minus r, we're going to have a squared equals h squared plus, we just FOIL it out, first, outer, inner, last. So we're going to have b squared minus br plus r squared, okay? Alright, so that gives us, what does that give us? It gives us a squared equals h squared plus b squared minus 2br plus r squared. Okay, now we're going to make the substitution of the values of h and r that we got earlier by applying for a triangle trig to triangle ABD. Okay, so we know that h is c sine A and r is c cosine A, so we're going to plug in those values into h and r here. Okay, so let's go ahead and make that substitution. I'm going to color code it so we don't get confused. So we're going to have a squared equals, instead of h, I'm going to replace that with c sine A, and put that in blue, c sine A square. How do I know that's the case? It's up here, there's the value of h, plus b square minus 2b, instead of r, I'm going to put c cosine A. Let's put that in green, c cosine A. Okay, and then plus r squared. R squared, r is c cosine A also, so we're going to do c cosine A squared. Alright, so from here on out, we just use arithmetic and then Pythagorean identity, Pythagorean identity to finish this off, okay? Alright, so let's simplify this. We have a squared. Now, how do you expand c sine A? Well, you just basically distribute this square to the c and the sine A, yes? So that basically becomes c squared sine square A. Okay, that plus b squared minus 2, we just distribute this, 2bc cosine A. And then for this one right here, we distribute this just as we did with the square here. We're going to distribute this square to the c and the cosine A. Okay, so the c and the cosine A. Now, alright, so if we do the distribution, we're going to have plus c squared cosine square A. Okay, now let's bring the the square trig functions next to each other. Okay, so I'm going to rewrite this as a squared equals c squared sine square A, and let's bring this next to it, plus plus c squared cosine square A plus b squared minus 2bc cosine A. Okay, now look, focusing on these two right here, these two trig functions, I can factor out c squared because they're common in the first two terms with the square trig identity. So I'm going to have a squared equals, factor c squared out, we're going to be left with sine square A plus cosine square A plus b squared minus 2bc cosine A. Okay, so remember the trig identity I showed you earlier, the Pythagorean identity for sine and cosine. Remember, sine squared theta plus cosine squared theta equals 1, right? So we're going to make that substitution here. This entire piece is basically 1. So we're going to have a squared equals c squared times 1 plus b squared minus 2bc cosine A. Okay, now let's rewrite this. We can write this as a squared using the commutative property of addition, as equals a squared equals b squared plus c squared times 1 is simply c squared minus 2bc cosine A. Okay, so there goes your law of cosines in terms of A. All right, remember there are three variations for this. All you just have to do to establish the others are true is just alter the lettering, and then you end up with the B case, the B squared case, and the C squared case. Okay, so this could be extended to the other two cases. So by altering uh, the order of the alphabetical labels, uh, this proof can be extended to show that um, b squared equals a squared plus c squared minus 2ac cosine b, and c squared is equal to b squared, let's call it a squared plus b squared minus 2ab cosine c. Okay, all you just simply do is you just switch the order of the alphabet. So instead of starting with A, if you start with B, you end up with this one. Like we have a right triangle right here, we just start with, call this B AC. And then the other one, if you start with C, for the other case, then you have this. So just by altering the order of the labels, we can end up with these other two laws of cosine. Okay, so there you have it. So thanks so much for taking the time to watch this video. Please feel free to subscribe to my channel by clicking up here. And if you like this presentation, please click like. And please post a comment. Tell me what you think about this presentation. I really appreciate it. More clips can be found on mythirdshift.com. Thanks again and have a wonderful day.